All right, start with fixing this typo. Notice here I have a place for two parts of the second derivative test, and they both say if f prime of c equals 0 and f double prime of c is less than 0. You make that first one. It doesn't matter which one you change, but change one of them to positive. We'll change one of them to f double prime of c is greater than 0. Okay, so remember the first derivative test gives us a way to use the behavior of f prime to tell us where the local minimums and local maximums, the relative extrema of f are. And the second derivative, you may have guessed, lets us use the second derivative of f to tell us about where f's local mins and local maxes are. So remember that the only possible locations for relative extrema are at critical points. So we still have to know about critical points, which always is going to require we find the first derivative anyway. But if I have a critical point at C, and I know, I'm looking at this first line here, I change this one to greater than 0, so just make sure that yours matches. If f prime of c is equal to 0, so if there's a critical point, if f has a horizontal tangent at C, and f double prime of c is positive, then what can we conclude? Well, just remember, f prime of c means there's a horizontal tangent. If you try to draw the tangent line, you could. So the tangent exists, the slope exists, the derivative exists. And f double prime of c is greater than 0. We just learned about that. It means f double prime of c, that means the function is concave up at c. So if there's a function and at c it's concave up, and I can draw in a tangent line, a horizontal tangent line, then I have to ask myself right there at that dot at c, what kind of relative extreme value do I have? Well, you can tell that that's a relative minimum. That's what makes the bottom of a valley. You have a horizontal tangent, a tangent that exists, a horizontal tangent, and on top of it, the function is curving up like a bowl. So this here, relative. And just so you know, to be perfectly honest, when I use the second derivative test, because sometimes I do that on a Saturday night, when I use the second derivative test, it's not that I have that line memorized, but I ask myself about concavity. I say, okay, well, I know I have a critical point, I know my f prime equals 0, and I know my second derivative is positive. That tells me this function is concave up, and I think of this picture, and that's when I remember, oh, well, if this is concave up, the extreme value is that bottom of the valley. So bottom of the valley, relative minimum. Similarly, if I have a place on my function where I can draw a horizontal tangent and the second derivative exists and is negative, it means my function must have been concave down. What kind of relative extreme value am I going to have? Here's concave down with a horizontal tangent. What kind of relative extreme values? That's a local maximum. Remember, another exactly equivalent thing to what I just wrote is local maximum. You could write, instead of that word relative, you could have written the word local. It means exactly the same thing. Okay, so here's what we know. Here's what you don't know. Sometimes you won't actually be able to evaluate, you won't actually be able to tell whether the first derivative changes sign. So there's some times where you won't be able to use the first derivative test, but you can use the second derivative test to decide if a function has a local minimum or a local maximum, or neither at a certain point. Well, that's the part I didn't mention. Notice here, if I have a critical point, not a critical point where f prime is undefined, because if f prime is undefined there, I'm not going to be able to find f double prime, so there's no second derivative to use a second derivative test on. But if I have f prime equal to 0 at some critical point, either the f double prime is going to be positive, the function was concave up, and I'm going to have a relative minimum. Or the function was concave down, and that means because f double prime was negative, and up there I have a relative maximum. There are two other possibilities. You could have f double prime equal to 0. 0 is neither positive nor negative. If you end up with a second derivative of 0, then the second derivative test is not conclusive you're probably going to find out that there is no relative extreme value there because it doesn't meet either one of these criteria. The last possibility is that the second derivative might be undefined even though the first derivative is defined, in which case you're going to have to find another way to decide whether your function has an extreme value there. Okay, so take a look at question 4 from 2004. It's a good example of how you might be able to use the second derivative test in a place where the first derivative test isn't going to help. Parts A and B are really super excellent review. And you might see problems like this in your free response book, so I want you to pay very close attention. And then by the time we get to part C, that's where we're going to need the second derivative test. All right, so I have a relation. I don't know that it's a function. There's a good chance it's not a function. That doesn't look like I'm going to be able to isolate the y. But I can still find dy dx. And look at this friendly problem. They told you the answer. We just have to not mess up the math and show that we can actually arrive at that answer. So how can I find dy dx when I don't have y explicitly defined? I use implicit differentiation. So I wrote my original equation here. I'm going to take the derivative of both sides of this equation with respect to x. This is going to be 2x plus the 2 multiplies to 4 to make 8y. I could write dy dx. Hope you don't mind. I'm going to use y prime here. It's a little easier than writing dy dx with my finger. The derivative of 7 is 0. When it's time to take the derivative of 3xy, I'm going to have to use the product rule. I'm going to imagine a dot right there. 3x times y. So the derivative is going to be the first, 3x, times the derivative of the second, which is y prime, plus the second, which is y, times the derivative of the first, which is 3. Now my goal is to isolate y prime. I'm going to move all the y primes over to the left, and I'm going to try to move everything that doesn't have a y prime to the right. I'm going to end up with 8y y prime, which was already there, minus 3x y prime, equals the 3y that was there minus this 2x. Notice I can factor out y prime. It's going to be y prime times 8y minus 3x equals 3y minus 2x. And I'm going to isolate y prime. That's another name for dy dx. That's going to come from dividing both sides. I hope you don't mind imagining this last step. Divide both sides by 8y minus 3x. That's how I'm going to end up with a final answer of y prime equal to 3y minus 2x over 8y minus 3x. You could have answered this question with more steps or fewer steps, but absolutely positively you would have to have this step here where you show that you've taken the derivative of both sides with respect to x. After that, if you do some of this algebra in your head to isolate y prime, they're not there to check your algebra. They want to know that you knew how to do implicit differentiation, which is this line, and that you know enough algebra that you can isolate y prime, whether that takes you 10 steps or you do it in your head. That's fine. They're looking for this final answer. Okay, so now that I have y prime, and notice, even if you couldn't do this, even if you made an error somewhere in part A, when it's time to do part B, you know what dy dx is, right? Because they've told you the right answer. So even if something goes wrong with your implicit differentiation and you can't arrive at part A, continue on with part B. You're going to be able to answer part B and part All right, so part B, show that there's a point P with x-coordinate 3 at which the line tangent to the curve is horizontal. Find the y-coordinate of P. So they're saying there's some ordered pair on this original function, xy, and the x is 3, and at that place, there's a horizontal tangent. So we have to figure out, when does a function have a horizontal tangent? Well, tangent, the slope of the tangent is the derivative. We need the slope of the tangent to be 0 because horizontal lines have slope 0. So I need my dy dx, which is 3y minus 2x. Even if you got it wrong in part A, you look at the answer they gave you to get it right, 8y minus 3x. I need that to equal 0. Well, when is a fraction equal to 0? When its numerator equals 0. So I know that 3y minus 2x must equal 0, and I've been told, it's kind of them, that x equals 3. So 3y minus 2 times 3 equals 0. Again, feel free to show as many or as few steps as you like here. It tells me that 3y equals 6, so I conclude y equals 2. I've been asked to find the y coordinate of p. The y coordinate of p is 2. All right, so now it's time for part C. I wrote myself a reminder up there that the point I found in part B was 3, 2. The 3 was given to me, and I just figured out that the y is 2 from part B. So I'm asked to find the second derivative, the value of d squared y dx squared at 3, 2. And then there's some questions for me to answer. So I know dy dx, I'm going to call it y prime just for convenience here. 3y minus 2x over 8y minus 3x. And I'm going to need to find the derivative of y prime. So the derivative of dy dx is d squared y dx squared. So I'll write this out, d squared y dx squared. Notice y prime in that first line I wrote here is isolated. So I don't have to use implicit differentiation here. I'm going to have to use the chain rule for sure. Okay, so now it's going to be time to take the derivative. I'm going to use the quotient rule. The derivative of this giant fraction is 8y minus 3x, that's low, times d high. D high is 3y prime minus 2 minus 3y minus 2x times the derivative of the denominator, which is 8y prime minus 3, all over 8y minus 3x squared. So that's, let's see if I can do this. Low d high minus high d low all over low squared. All right, so this isn't quite as bad as it looks because I just want to get a one number answer here. And really, all that matters is I can simplify it enough that I can tell whether it's positive or negative. So just notice I have some things to replace, right? I know I can replace all my x's with 3's, all my y's with 2's. And there's one other variable in my expression, and that's y prime. So what I need to know is what is the value of y prime when x is 3 and y is 2. So I'm going to just write myself a little note here because it's going to make the substituting in to this giant expression a little easier. At the place where, so y prime when x is 3 and y is 2 equals 3 times 2 is 6 minus 2 times 3 is 6. All over 8 times 2 is 16 minus 3 times 3 is 9. Doesn't matter so much because 6 minus 6 makes 0. So now I'm going to go back to my second derivative. I'm going to call it y double prime just for, so I don't have an extra fraction. One more thing to write on 2 lines. And I'm going to try replacing these values as they show up. Everywhere I see y prime, I'm going to replace it with 0. Everywhere I see x, I'm going to replace it with 3. Everywhere I see y, I'm going to replace it with 2. So here I go. 8 times y, 8 times 2 is 16, minus 3 times 3 is 9. Multiplied by, that's 3 times y prime, but y prime is 0, so 0 minus 2. And I have my subtraction sign. 3y minus 2x, that's 6 minus 2 times 3 is 6. Oh, that's nice that that showed up. Again, there's a big 0, so I don't even care what this is because I'm going to multiply it by 0. And that's all over 8 times 2 is 16 minus 3 times 3 is 9, all squared. All right, I switched to purple and I'm coming all the way up here. Y double prime at 3, 2 is going to equal 16 minus 9 is 7. Whoops. 7 times negative 2 minus, that was all 0 after the subtraction sign. And in my denominator, 7 squared, 49, which I could simplify, you have no obligation to simplify, to negative 2 sevenths. All right, so I just found out that, my pen, d squared y dx squared evaluated at the place where x is 3 and y is 2 equals negative 2 sevenths. And I have then a next question. Does this curve, that curve, the original curve, have a local minimum, a local maximum, or neither at the point P? So most of the time when you see a question about a local minimum or a local maximum, you're going to think of the first derivative test. You're going to think, I'm going to figure out at the place where x equals 3, does y prime change from positive to negative, in which case there would be a relative maximum? Does it change from negative to positive, in which case there would be a relative minimum? Or does it not change sign? Or was 3 not even a critical point, in which case it would have neither? So what we are going to have to notice is that we don't have enough information. We don't actually, because y prime is a function of both x and y, we don't know what happens to y prime when x equals 3, because y could be changing at the same time. So our only option here is to use the second derivative test. So what does the second derivative test say? At a critical point, the place, in this case, at the place, oh, I didn't write, I erased it, it was 3, 2. If f prime, if the derivative is equal to 0, so in this case is y prime at 3, 2 equal to 0. Well, we figured that out on the last slide, right? When we wanted a shortcut for what would we plug in for y prime when x was 3 and y was 2, and we did in fact get 0. This part works. So if the first derivative evaluates to 0, and the second derivative, in this case the second derivative is negative, that tells me that the curve is concave down at this point, 3, 2. What kind of relative extreme value am I going to have? Well, I definitely have a horizontal tangent. That was what part B was all about. Horizontal tangent. And I have a function that is concave down. What kind of relative extreme value is there? That is a relative maximum. So I'm going to write up my final answer. So this is what I wrote. I wrote myself a little note. The point P was the point 3, 2. I wrote, since dy dx evaluated at 3, 2 equals 0, and d squared y dx squared evaluated at 3, 2 equaled negative 2 sevenths, which is less than 0, the curve has a local maximum at point P.